Let me share screen. So can you see my screen?
Yes, sir.
Okay, good. Okay, let me start new class. All right. So we will start with the idea of mean squared error. One of the very popular notion, not only in statistics, also in the domain of machine learning. So we will spend a little bit time on this. So if W is an estimator of parameter theta, then MS mean square error of W is expected value of W minus theta whole square with respect to theta. Now, one concept is called unbiased estimator. It says that if W is an estimator of theta, can you please if you don't have any question? If W is an estimator of theta, then of W equal to theta. And then bias of W is defined as you can say bias of W with respect to theta is expected value of W minus theta. Sometimes it is also written as expected value of theta. W is theta plus bias. Now, of course, if it is unbiased, then this will be 0 if W is unbiased. So bias is 0 if W is unbiased, otherwise some PL number. Now, you can ask me Can bias be a multiplicative? And the answer is yes, it can be multiplicative as well. So, but we will explore it little later. One small result to explore is you can write mean square error of W as variance of W plus bias of W square. So that means expected value of theta, W minus theta whole square equal to variance of W with respect to theta plus expected value of theta W minus theta whole square. Okay. Now, can anybody tell me how can we check this result? So we can write this as so we can check it, we can write the mean square error of theta W with respect to theta is this guy. We can write this guy in a slightly interesting way, in a sense that we can write it in this way. W minus expected value of W plus expected value of W minus theta whole square. Okay. Now I will treat this as A and this as B. Then it's a A plus B whole square kind of formula. So I kind of write it as expected value of W minus expected W whole thing square plus E theta minus W minus theta square plus 2 into W minus E theta W whole square, sorry, times E theta W minus theta. Okay. Now we can write this as expected value of W minus E theta W whole square plus E theta W minus theta whole square plus 2W minus E theta W times E theta W minus theta. So this is effectively variance of W plus bias of W whole thing square plus these product terms. So if we can show that if we can show that the third term, the product term is 0, that 2 times W minus E theta W times E theta W minus theta. This whole thing is 0, then we are done. Can you show that? There is an expectation, yeah. So, yeah, there is an expectation. Can I leave it for you to check it out? Guys? Hello?
Yes, sir.
Are you guys there? If I am asking question, please respond. Huh?
Yeah.
Sure. Okay. So let us try an example. So x1, x2, xn, normal, mu sigma square. Now x bar equal to 1 by n summation xi, and s square is 1 by n minus 1 summation xi minus x bar square. Okay, and you can show that expected value of x bar equal to mu, and variance of x bar, which is expected value of x bar minus mu whole square, is sigma square by n. Similarly, expected value of a square, in a previous class we have shown that this is sigma square, and variance of a square, which is expected value of a square minus sigma square, is 2 sigma to the power 4 by n minus 1. Now see what happens since both of them are unbiased estimator. Unbiased estimator. The mean square error of x bar is same as variance of x bar, because bias is 0. Bias of x bar is 0. Similarly, mean square error of a square is same as variance of a square because bias is 0 again. Now, what I will suggest, can we consider, let's consider maximum likelihood estimate of mu and sigma square. Now, MLE of mu is x bar. So our problem is solved, but MLE of sigma square is different. Is small s square, it is 1 by n summation xi minus x bar whole square. The unbiased estimator that was proposed, it had divisor 1 by n minus 1, and here it is 1 by n. So it's slightly different. So that means effectively my smallest square, I can write it as n minus 1 by n a square. Correct? So MLE of sigma square is this small s square. The first thing I will check whether it is an unbiased estimator or not. So expected value of s square is same as n minus 1 by n expected value of big S square. I do know expected value of a square is sigma square because a square, capital S square is unbiased estimator. So turns out n minus 1 by n equal to sigma square. So this is same as 1 minus 1 by n sigma square, or sigma square minus sigma square by n. So this is my bias. Okay. So that means MLE of sigma square is a biased estimator. That is an interesting phenomenon, because unbiased estimator is something naturally probably we would look for, but here we are seeing an example where maximum likelihood estimator turns out to be a biased estimator, and we can say that it is actually underestimating the sigma square. It will, on an average, it will little bit underestimate the sigma square. So shall we use it or not? Question is this. In such situation, we have to look for whether there is a bias side, there is a variance side, or there is a mean square error side. So let's look for mean square error for sigma square or a square. Now mean square error, MSE of a square, which is also MLE of sigma, is expected value of a square minus sigma square whole square, which is a square is again n minus 1 by n. So we can write it as variance of a square plus bias of a square. Now what is very smallest square? Smallest square is n minus 1 by n capital S square. Okay. And bias is n minus 1 by n sigma square minus sigma square whole thing whole square, because this is bias square whole square. Now n minus 1 by n, this entire thing square, variance of s square plus n minus 1 sigma square minus n sigma square by n, this whole thing square. Now variance of a square, we have checked it out previously, is 2 sigma to the power 4 by n minus 1 to, so n minus 1 whole square by n square, 2 sigma to the power 4 by n minus 1 plus, so in sigma square and sigma square cancels. So we are left with sigma square, sigma to the power 4 by n square, and this cancels. So so we will be 2n minus 1 by n square times sigma to the power 4. All right. Now we have this mean square error of small a square is expected value of a square minus sigma square whole square. So we can clearly write 2n minus 1 by n square times sigma to the power 4. Now clearly this one is less than 2 by n minus 1 times sigma to the power 4, which is expected value of capital A square minus sigma to the power 4, which is mean square error of S square. So turns out though maximum likelihood estimator of A square is an better property in a sense that mean square error is less. Okay, so though MLE of sigma square is a biased estimator, mean square error of A square is less than mean square error of unbiased estimator, which is A square. What does it mean? So it means MLE, we are doing a little trade-off between bias and variance. So in MLE, we are accepting a little bit of bias, but that is helping us to reduce the variance, and in total mean square error is getting reduced. So even if, so that means even if MLE is systematically MLE of sigma, MLE of sigma is systematically underestimating the sigma square, because we accepted little bias, but overall MSE is being reduced by reducing variance of the estimator. So that means even if that is on an average, a square is closer to sigma square. Okay, so
Sir, I have a question.
Yeah.
Sir, then I mean, when is like MLE is more useful than unbiased estimator? I mean, everywhere we need to estimate something unbiasedly. I mean, we should use the unbiased estimator. Why is MLE more useful? I get that variance is less, but when it is useful in this context.
Why you think unbiased estimator is always useful? Why you need estimator has to be unbiased?
I mean, so that the estimate is unbiased. I mean,
No. You
that
can have a estimate, unbiased estimate, but it has a very high mean square error. What does it mean? Means, okay, let me give you a situation. Tell me which one you'd like. So here is the true theta. Okay. You are estimating it with the theta hat. So theta hat sometimes would be here, sometimes theta hat would be sometimes here, sometimes here, sometimes here, sometimes here. Okay. And theta hat is unbiased. So the overall sampling distribution of theta hat is something like this. Now you come up with another estimator. Still theta naught is here, which is say theta tilde. And you know it systematically underestimate the theta naught or theta. So, but most of the time turns out it gives you estimate here, 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 here. So that means you have something like this. Which one would you like to use, theta hat or theta tilde?
Sir, in this case, the mean, the peak is shifting to a bit to the left in case of MLE. I am still getting confused. Means why should we use this? I mean, we in case of the unbiased estimator, we are getting the peak.
Wait a minute. You did not answer me. I have a very specific question. Theta hat is an unbiased estimator. Theta tilde is a biased estimator. Which one would you prefer?
So from the diagram, it seems the MLE is better.
I don't even tell you it is MLE or anything. I'm just saying that there
I
are
mean,
two.
yeah, means yeah, this the
The
second one.
biased is better. Why? Because on an average, we in real life we never know where is actual theta naught. Right? My estimator will be only as best as my sample, whatever I have observed. Correct? So I would prefer an estimator which is on an average close to the my true parameter. I really don't know which one is which one is, I mean, biased or unbiased. Even if I get a theta unbiased estimator, still I will incur certain degree of loss. Some error will be there. If I'm observing this observation, I like it or not, this much of error I have committed. If I'm observing this observation, this is where my estimate is. I like it or not, this is my error. And the philosophy is, when I'm estimating, end of the day, I don't know where is my true theta naught. So what can I do? I can do best. I would like to reduce overall error. This error. That is where the main focus come in.
Yes, sir. Means I see that the variance is less in the biased estimator case, but it is underestimating the parameter.
Why are you so bogged down with biased and unbiased estimator? Because it was being taught to you. That is very important, right? By
Yes.
your undergrad. Yeah, I know that. I am coming from the same school. I know that. It took a lot of time for me to unlearn this, things. Particularly, Professor Cramer-Rao invented this unbiased estimator and mean variance unbiased estimator. So people really get bogged down with, particularly students from India. They get agitated if it is a biased estimator. Why are you getting so bogged down with that? Focus on what we are trying to achieve. What is more meaningful? What is more logical? The logical thing is, I have an estimator and I want to estimate a parameter, and whatever I do does not matter. If I have a random sample, my estimate is based on a certain sample, I will occur certain error. I like it or not. What I can try, I would like to reduce those error as much as possible.
That should be the goal. Overall error can be as minimum as possible. Now, having said that, if you can figure out that this particular estimator generally try to underestimate the bias or something, right? Underestimate the real thing. If you have some sense of bias, then you can try to correct for the bias. That you can always try that, but that's a difference. And then that's a right step forwards. And when you will see, we will get into a little bit of bootstrap statistics, you will see that we will do those kind of corrections. Because first step should be you get an estimator which reduce the mean square error to an extent. And then if you feel that there are two kind of bias which is manageable systematically, okay, I'm okay with 1% or 2% bias, underestimation or overestimation, whatever is happening. But if it is 10%, 15% underestimation is happening, that's a lot of bias. And then we can think of to developing a methodology, how can we make correction for those bias. But the problem is if you constrain yourself within the class of unbiased estimator, then you will never explore biased estimator and their properties like this one. In this case, like this one, there is a mean maximum likelihood estimator whose mean square error is less than the unbiased estimator, that it is little bit underestimating, but overall mean square error is less than the unbiased estimator. In fact, the overall mean square error is less than this square is minimum variance unbiased estimator, MVUE. We will get into this MVUE concept very soon. This S square has a special property called minimum variance unbiased estimator. And typical statistics department, they just beg their head finding minimum variance unbiased estimator. Okay, but the problem is if you only focus on minimum variance unbiased estimator, then you are completely losing out the class of estimators which you can induce little bit of bias, but it can bring hell lot of reduction on overall variance, right? So, and that is where the concept of variance trade-off between bias and variance comes in. In machine learning, almost every book or every course on machine learning spend a lot of time in this one. Trade-off between bias and variance. Why? Because people do know that if you only focus on unbiased estimator, then you are completely ignoring lots and lots of other estimators. Another reason why people think of this trade-off between bias and variance is this. Going forward, when we will explore more and more complicated problems, for example, neural network, or neural network, then CNN, all kind of neural network and etc. These models are typically so complicated. They will have bunch of parameters, and these complicated neural network models are so complicated that finding unbiased estimator is simply out of question. Then you have to rely on this kind of maximum likelihood estimation method or regularization and all these things. So unbiased estimator is a cute concept, but it has limitation. The limitation is you can find unbiased estimator only for some limited toy examples which are available in the book. In more recent models, recent problems which uses much more complicated problems, like if you study survival analysis, if you are studying Cox proportional hazard models and stuff like that, which are much more complicated models, they're finding estimators and oftentimes is very difficult, and then finding unbiased estimator for that is even harder. Okay, so that is where we are more focusing on reducing mean square error rather than focusing on finding unbiased estimator and then reducing variance. So the minimum variance unbiased estimator is a topic everybody in stat community loves. Variance unbiased MVUE. And pretty much every stat department, every stat professors go bang on this concept. But here is, and what this concept is talking about. The concept is talking about if W is an unbiased, W is known as minimum variance unbiased estimator of theta if two things. One, expected value of W is theta, that means W itself is unbiased estimator. And the second thing is if U is an unbiased estimator, that is if U is another estimator, U is another estimator of theta such that expected value of U is theta and variance of U is greater than equal to variance of theta. Sorry, W. Variance of W. for all U for any other estimator of unbiased estimator. So what is this minimum variance unbiased estimator is telling you? Minimum variance unbiased estimator is telling you among the class of unbiased estimator. So U is another estimator which is also unbiased. Among the class of unbiased unbiased estimator, W is the best, which is good thing. Finding a minimum variance unbiased estimator is a good thing, but the problem is different. Problem is much larger. What are you are missing out a much bigger problem. The problem is your class of estimator could be is here. This could be your class of estimator. The entire universe or omega of estimator. Now suppose you can divide this estimator into two parts. One is on class of world of unbiased estimator, and here is the world of biased estimator. You are saying what this minimum variance unbiased estimator is saying, among the unbiased estimator, all the estimator that you have, you find the one which has the minimum variance, because you don't have to worry about the mean square error, because since it is unbiased estimator, MSE is equal to variance. So you reducing the variance is same as reducing the mean square error. So inherently, you are reducing the mean square error, because this variance is your mean square error, you like it or not. This variance is your mean square error of U, and this variance is your mean square error of W, because your bias is 0. You are reducing variance means you are reducing mean square error, but you are reducing only in the class of unbiased estimator. And you are simply not exploring the entire rest of the world. Okay. So that is why in machine learning, people are saying that, well, minimum variance unbiased estimator is anyway estimating, reducing mean square error. So if I'm reducing mean square error in any way, why bother classifying myself within an unbiased estimator? I rather might consider the entire world of unbiased estimator, world of estimators, find the best one which has the minimum mean square error, and then if there is a systematic bias and the bias is too large, then we can think of how to reduce that bias. But end of the day, if I can find an MSE which may be a little MSE of an estimator, which may be a little bit of bias is less than the MSE of an unbiased estimator, okay, I'm already one step ahead, in a sense that here what is happening here, I have variance of W plus this bias of W square, and this is what is happening. This is effectively variance of W plus 0. My bias is 0. That is what is happening. So then, if I can already, if I'm exploring in the whole world of estimators, then and if I find W, which is already better than from mean square error perspective, because end of the day variance of W is same as mean square error of W, and I'm getting a mean square error. So basically this is what I'm happening. My mean square error of W is less than mean square error of U, which is effectively variance of U. My bias is 0, and U is suppose my minimum variance unbiased estimator. If I can find a W which is whose mean square error is less than mean square error of MVV, I'm already one step ahead. And then what I can do, I can look into bias, how much bias it is. If it is unacceptable, then we can try to do some correction for bias. Okay. So this is the idea typically ML approach takes. Now the question is, not all the time I will be able to find estimator mathematically closed from estimator.
Sir?
Tell me.
So can we say that if an unbiased estimator has a constant CV, that is the CV is free of unknown parameter, then there can exist a biased estimator of the same parametric function, which is better than the unbiased one?
I didn't get your point. Can you, what do you mean by CV?
Sir, a coefficient of variation?
Okay.
Sir,
What do you
I'm saying
want?
that, if an unbiased estimator has a constant CV, that is the, I have an unbiased estimator and then I calculate the CV, theoretical CV, and it is free of the unknown parameter. Then can we say that there always exists a biased estimator of the same parametric function which we are trying to estimate, which is better than the unbiased one?
I have to think about it. I don't know what kind of logic that is coming from this.
So say like I try to do this problem in this way, like say T is an unbiased estimator of theta. And we define T star equals to say some constant C into T.
Okay.
And then MSE of T star will be some say psi of C, and then I'm trying to like minimize this psi C.
Okay. I have to look into it. I'm out of the head. I cannot make a comment on this. Can you please write it down and send it to me?
Yes, sir. Yes, I'll do.
Yeah. Okay. So I am now proposing a problem. The problem is something like this. So oftentimes what happens, I have a model. Okay. So suppose and some y tilde, say y1 to yn, follow some model which has certain parameters. Okay. Now I come up with two different method of estimation. Two different method of estimation. Say one method gives me theta 1 hat and another method gives me theta 2 hat. Okay. Now the problem is this model is so complicated. The model model M is so complicated that we cannot find mean square error. We cannot find analytical form of mean square error. Find the analytical form of mean square error, unbiased estimator, bias, variance, anything. Okay. How can we compare theta 1 hat and theta 2 hat? Any idea?
So can we take a random, generate a random sample and then check for these two estimators, the bias variance and MSE?
Yeah, that's pretty much what people do. So people resort to Monte Carlo. It is called Monte Carlo simulation study. Typically study. So what people do that they assume some true value of theta naught. Okay. So theta equal to theta naught, and then given the theta naught, you can simulate y1, y2, yn from this model. Suppose I call it y1 star tilde. And then you estimate theta 1 hat star, theta 1 star, and theta 1 2. Sorry, the 2 1 star using y1 star. Then you generate another sample y2 star, y1 star, y2n star from the same model with the same parameter theta naught, and you estimate theta 1 2 hat star and theta 2 using y2 star. Similarly, you draw y3 star equal to y1 3 y
This is coming from the model theta naught. And then again estimate theta 1 3 star hat star and theta 2 3 hat star using y3 star, and you continue in this way so many times, which is m1 star m star from the same model theta naught, and then estimate theta 1 m star theta 2 m star using y m star. Now what you can do, you can calculate this is Monte Carlo estimate of expected value of theta 1 hat minus theta naught whole square. Similarly, 1 by m summation m equal to 1 to capital M theta 2 m star minus theta naught whole square is approximately equal to expected value of theta 2 hat minus theta naught whole square. This is, and then you have this, you can compare the mean square error of theta 1 hat and theta 2 hat, and you know which one is better than both. So this is typically the Monte Carlo method that people do use. All right. Now I will talk about, I have talked about minimum variance unbiased estimator, and next I'm going to talk about something called an interesting, a very popular theorem in mathematical statistics called Cramer-Rao inequality. Cramer-Rao inequality. So let x1, x2, xn be sample with PDF f of x theta and let wx tilde is some parameter, some estimator, sorry, x1 to xn, be any estimator, estimator satisfying d of d theta e theta w of x tilde equal to integration by delta theta wx tilde f of x given theta dx
tilde. And so this is the first condition to check. And the second condition is variance of W x tilde with respect to theta is finite. If these two conditions holds true, then variance of Wx tilde is greater than equal to d of d theta e theta of Wx tilde, this entire thing whole square divided by e theta del theta log of f of x tilde given theta whole square. Now, what does it mean? Let us just focus on the statement. This is the statement of the theorem or statement of the inequality. I'm not going into the proof today. It's almost end of the class. I'm not going to, proof is there in page 336 at Castleberger. So proof in page 336 in Castleberger. So what is it telling us? That first thing, if Wx is an unbiased, if Wx is any estimator, if Wx is any estimator which satisfy this condition, what is the physical meaning of this condition? Remember that this expectation is nothing but an integration.
Sir, the parameter space has, the range has to be free of the parameter space.
What do you mean by range? Has to be free of parameter space.
So the support of the random variable has to be free of the parameter space.
What?
Sir, if the range, if the support of the random variable here, it's like it's x or chi you have written in under the integral, that's the support of the random variable, right? So if that contains the unknown parameter theta, then we can't transfer the differential inside the integral. We'll need Leibniz rule for that. So that is one condition, right? Like you are asking for the physical interpretation.
So let's take x follow normal mu sigma square. Okay. X is following x. What is the support of x? Real line. What is the support of mu? Real line. Now,
Yes, sir.
are they inside one of each other?
No, sir. Say we have say uniform theta and say theta 1 comma theta 2, uniform theta 1 comma theta 2. So the support of the random variable will be between theta 1 and theta 2, open interval theta 1 and theta 2. In that case, this condition won't hold.
That is not even differentiable.
Yes, sir, that's what I'm saying. Like
that is not even differentiable. Okay. So that's a very trivial example that you give. I am saying here even simpler. I am not even going into that complicated level. I am saying very simple that this expectation is nothing but an integration over chi. Are you with me on this?
Yes, sir.
Okay. And then they here basically the differentiation is after integration, and here you're taking differentiation before integration, and that too will match. It's basically switching the double integration or the switching the differentiation integration, that rule. Okay, so this condition will hold. All it is saying that this condition is hold, and then of course variance is finite. Though it is written as an expectation, you have to remember whenever it is expectation, it is nothing but an expectation is nothing but an integration. So on the left side, you are taking the differentiation before the integration and sorry, after the integration. Once first you're doing the integration and then you are taking the differentiation. On the right side, first you're doing the differentiation and then you are taking the integration over chi. Differentiation is always on the parameter space, and integration is on the chi space, that is on the space of the random variables. But the order is different. So that means in which order you do, it is not going to affect my result. That is the only thing it's talking about. But remember that differentiation has to hold. So the uniform theta 1, theta 2 example that you gave me, differentiation doesn't even hold there. So this application of these result in that form is not applicable. This result is not applicable in that kind of problems. So this result is applicable to the class of distributions or the class of problems where, first of all, differentiation of parameter space holds and integration is also holds on the random space. That means it's a proper probability distributions and the order is not going to affect. That's all it's talking about. Now, having said that, and variance is finite, of course, that's a good thing. That's a bare minimum thing. It's saying that given a fixed sample size, effectively, variance of, given this set of variance of an estimator will have a lower bound. So you can try lot of things, but end of the day, it is bounded. You cannot reduce variance to an extent where, to whatever extent you want. There is a lower bound in the variance and you have to accept it. So that means, what is the meaning of variance of an estimator has a lower bound? That means certain degree of margin of error we have to accept. So variance of Wx means effectively if here is my theta naught, I cannot, so sometimes my W will estimate here, sometimes W will estimate here. If I'm very lucky, it will be very close to theta naught, but there will be some degree of error. But so that means there will be some margin of, so this distribution of Wx, this is the distribution of Wx or sampling distribution of Wx will help me to get certain degree of margin of error. And this variance of Wx has a lower bound, means this margin of error, you cannot reduce this margin of error to your free will. There is a certain degree of margin of error, at least we have to accept. We can do a lot of things and it can be reduced to an extent, but it can be reduced up to this level, not more than that. So there is a lower bound of the margin of error, and this margin of error we have to accept. We have to live with that degree of margin of error, which we cannot reduce indiscriminately. It doesn't matter how sophisticated methodology you are using, there is a margin of error, and this margin of error will have a lower bound, and this lower bound tells us that that bare minimum margin of error we have to live with. We cannot reduce our margin of error beyond that. But of course, our best methodology will try to achieve the variance of Wx to be the minimum bound. So that is what it's talking about. Okay, I think we'll stop here. I have assigned an assignment, and so, and then I'll assign another assignment probably in a next week. But in between, try to solve those questions, and I will assign few more assignments. And if you have any question, please drop me an email. Okay, all. Thank you very much.
Sir. Sir, I had some questions regarding the last lecture, and
Okay.
I had emailed you. So if you can check it. Like
Yeah, there's regarding that beta distribution thing.
Yes, sir. Yes, sir.
Yeah, that is correct. You have to little bit just figure out where, I don't know why you are not getting it. So the solution is fine, perfectly fine. You try to understand, try to solve it by yourself. If you can't, then let me know. I will give a more detailed explanation. Okay.
Okay, sir.
Okay, fine.
Thank you, sir.
Yeah.